All right. Well, hello everybody. I just want to welcome everyone to our talk today, the MP seminar. This is a joint sponsorship between the FDS Center and the APT Center seminar, or APT Center. Sorry about that. So today I'd like to introduce Dr. Tom Sugar, and works in the area of wearable robotics for rehabilitation and gait assistance. He's an associate professor in the Department of Engineering at Arizona State University Polytechnic campus. He earned his PhD, Master's, and Bachelor's of Science Engineering from the University of Pennsylvania, in addition to a BS in Economics from the Wharton School of Business Management and Technology program, which actually is a very cool thing. And we had a great conversation at dinner the other night. We got to talk to him about the IP discussion with the university lawyers, which was like... So anyway, let's see here. So, but that was also at the University of Pennsylvania. He draws from a wide range of funding sources, including DARPA, the NIH, the NSF, Army, and industry, which is, it casts a very wide net, which is very interesting. And his work has been highlighted by the media on ABC World News Tonight, the UPI, the New York Times Magazine, and in the National Geographic, just to name a few of those. So he's going to talk to us today about one of his current projects, the SPARKy ankle, the powered prosthetic that utilizes a spring-based robotic tendon. And Dr. Sugar and I had the opportunity to meet each other at a TATRIX technical interchange meeting. And really what we'd like to do is, he has really very beautiful and elegant technology. And what we're trying to do is try and get as much of a possible sort of collaborative avenues through, where we'd like to try and see where we can get this technology to mesh with neural interfaces. And so the idea is to bring him in and to get him embedded in this community so we can actually see if we can move forward on some really exciting joint sort of, see if we can move forward on some different projects. So there we go. And then just really quickly, we've got a super compressed schedule in the morning, so I'm going to have to do a hard stop at 9:30. So if you guys would be willing to help me out with that, that would be fantastic. And then we'll dip him off to a Skype conference. Thanks. So thanks very much.
So thank you very much, Paul. And again, we met. Troy Turner had a TATRAC meeting, and we met, and I thought it would be nice to show off our robotic ankles. So today I'm going to talk about designing spring-based robots for enhancing mobility. And the work couldn't have been done without my graduate students, Joe, Kevin, Matt, Jeff, Alex, Ryan, all worked on the SPARKy ankle. So my human-machine integration laboratory is focused on areas of designing compliant actuators. I did wearable robots for stroke rehabilitation with Dr. Jiping He, and myself, I've been focused on powered prosthetic ankles. So this is just one slide on saying that, I had worked in an upper extremity as well with Dr. Jiping He on a Rupert project where we just built a pneumatic exoskeleton for reaching and feeding. So we had, done some work in that area as well. But the main focus today is to be talking about this robotic tendon. So I'm going to take 2 or 3 minutes on just this picture, because if you understand this picture, then you'll understand the rest of my talk. So if you look at a orthosis, these are different orthoses. This is one you just put your foot into. This was supposed to put your shoe inside your shoe. This one you were supposed to just step into, and your shoe was supposed to get strapped on this kind of belt buckle system. But if we look at it all, we basically have an ankle joint and we have an actuator system. An ankle joint, actuator system, ankle joint, actuator system. And this actuator system is what I'm calling it a robotic tendon. And the key thing to think about is that I control the proximal side of the spring. The proximal side of the spring is closed loop control. The distal side of the spring is open loop. And so this distinguishes me from the other people, because this side I'm open loop. So what I like to tell people is, you set the mechanical system up, you set the dynamics up, and then you live with the behavior afterwards. So that's different than maybe what other people are doing. Other people want to control the ankle joint. They want to control this side of the joint. They want to control physically. I want to force you to follow a pattern. I do not force you to follow a pattern. So let me delve a little deeper. Basically, I have a motor, and it's going to translate this side of this spring, and I'll say, in the talk, I'll say the input side of the spring, and then I'll say the output side of the spring. So if I say input side of the spring, that's the proximal side. And if I say output side of the spring, that's the distal side. So I control the input side of the spring with closed loop control. The output side of the spring is open loop. I know the forces I want in Gait because I go to the Gait literature. I go to people like you and I ask, what are the forces that should be on the Gait? What are the positions that should be on the Gait? So I go to Gait literature and grab positions, grab forces, and then as a good engineer, I back calculate, because engineers we all back calculate, I back calculate how I would like this movement to be. So I do position control about this movement. This spring is specifically chosen for your body weight. And I'm going to translate this spring back and forth. So another 2 minutes on this. Think about a spring. If I can squeeze it, and then I can translate it over here and then dump the energy out. So it's called translating potential energy. So F equals Kx is a bad version of the equation. They shouldn't have taught you F equals Kx. They should have taught you about that it's really the relative position or the relative velocity is power. So the relative velocity is what's really important. So I want to move, I basically want to store energy in this spring, move it, dump it, and then give you the right forces at the ankle. And I argue that that's what you're doing. Your gastroc or soleus is pulling on this side of the spring. This is your Achilles tendon, and this side is open loop. So I'm going to talk today about this robotic tendon. I'll talk to you about my tibia-based controller. And I added an extra thing, and I'm hoping I definitely want to get here, which is I want to talk about my simple controller and how I think it would be very easy to add a peripheral nerve interface to it. So these are the three things. The robotic tendon, I do not use joint angles. I use elevation angles. And I think we've got a simple robot with simple interfaces that you can attach to quickly. So our goal for the U.S. Army was to develop a new generation of powered prosthetic devices based on lightweight energy storing springs. There's been lots of work in this area. People work on microprocessor knees. People are working on microprocessor ankles, but there's also powered systems. So I like to use the word bionic system. So I say these are microprocessor devices. There's the Biome now from iWalk, and Michael Goldfarb out of Vanderbilt has very, very good work with a combined ankle-knee device. And then we've got our own powered ankle. So how do I look at systems? I look at systems as I study the human being first so that I can design good compliant actuators. I use a continuous-based control approach. I do not use state-based control. And I'm always trying to study system efficiency because I need things to be wearable. I need things to be autonomous. So we have built the SPARKy prosthetic ankles. We've done some knee work. We've done 2 degrees of freedom ankles where you could take the actuators and if you pull them both up, you dorsiflex, you push them down, you plantar flex. And if you do this to the actuators, you get inversion and eversion. We've done orthoses. And we've done different types of ankles. We've done energy harvesting ankles for the Army as well. But we basically try to focus on the Gait data to tell us how to build the other devices. So if we look at the SPARKy ankle, it is a Maxon DC motor connected to a roller screw transmission. Roller screws are different than, there's ball screws, roller screws, lead screws. We're using the best devices you can out of Switzerland. We've got springs that are tuned for the body. There's an ankle joint so that you can actually, the motor pushes down for powered plantar flexion and picks the foot up during dorsiflexion or for swing phase. We use standard carbon fiber keels from the market. When I say lever arm, I'm basically saying these springs are pulling against a lever arm, which is pulling against the ankle. We have 150-watt motors. The only thing we have to control the device is an encoder on the motor and a rate gyro. We have ankle encoders, FSR sensors, other things just to collect data. But And if there's any quick questions, stop me. Otherwise, do some questions at the end. But I want to at least tell you, we've got an ankle joint, motors, and springs. Electronics, we build our own DSPIC microprocessors. We have MATLAB, Simulink Real-Time Workshop, auto-generate C code for the microprocessors now. So we design everything in a graphical Simulink environment and then auto-generate code down. There's a quarter, there's batteries for 3 hours worth of use. We have a battery about that big for 8 hours of marching. So let me I'd like to show a video first. So just to show off what we can do, we can walk. We think it's a very nice looking, smooth walking. We can walk on inclines, declines. As you watch, he'll walk down the stairs, then he'll take 2 nice steps and then continue down the stairs, and we believe he can do that nicely because of our continuous control system. We're walking on an incline, and this incline is constantly changing its angle, and we believe we can do that because we look at elevation angles versus gravity. We can ascend and descend stairs, do jumping and running. So the ankle is following his tibia motion, and the tibia motion tells us, I'll let you watch. The tibia motion tells us how to move the ankle. He's jumping on a rock, uneven terrain. I've got a larger video of that, and he jumps down. So we can go over absolutely uneven terrain. We can do that because the output side of the spring or the distal side of the spring is open loop, so we can manage uneven terrain. He chose that, and then I was told by people that that's actually quite normal because the non-prosthetic leg is kind of what you want to base yourself on. So you support yourself on that leg and then kind of lead. So they were saying it's not that. It's obvious that he did lead with this prosthetic leg because you want to balance yourself on your good leg.
Where was campus security?
Yes, exactly. They're somewhere else. Actually, he's the one who started jumping up and down and doing things. He's a risk-taking type of guy, so he wanted to hop around and do things. And I was a little scared the first time he did it, to be honest with you, because we didn't plan. We didn't say, "Hey, can we jump on rocks or not?" He jumped up there, and then we said, "Oh, this is a." We came down, basically, if you know the campus, we came down that bridge, and this rock is on the other side of the bridge. And so he jumped up on top of it. Let's see. There we go. The next thing I want to show is some running. This is running we were doing at West Point, but the thing I wanted to show you is when you, by measuring the tibia to tell us what to do, I think the exciting thing here is that when he stops, the robot stops. So he's running at about, we've done as high as 8 miles an hour, but this is about 6 miles an hour. So he's running, and then he'll stop. And the robot automatically stops. And that's just based on our control scheme. So let's look at the, and I think many of you are familiar with this, so I'll go quickly then on this. Let's look at human gait. Basically, heel strike, you've got a little bit of plantar flexion, but what I'm worried about is this dorsiflexion. So as the human being rolls over the ankle, we want to store energy here. You've got powered plantar flexion, so you have very fast plantar flexion movement with a high moment, which means you've got high powers. So this is really the hard thing to take care of. How can you have high velocities with high powers? So the highlighted region is the push-off region of gait. And if you were to have a passive system, you get very good-looking moments. But what you don't have with a passive system, because with this dark line, with the Soch ankle, you do not have the ankle movement. You don't plantar flex and then you don't pick up the toe. You have very low power. You have a late bump and very low powers, and you don't get the push-off power that you'd want. And so that's what I think the powered systems give you. The powered systems give you the push-off and they pick the toe up. So again, let's look at this area here. If you have high velocities and you have high moments, then you need lots of power. So basically, you've got this energy here that you'd like to store, and you'd like to store some of that energy for push-off. That amount of energy is not enough for the powered region. So I've got to put about 20 joules of energy into the step every gait cycle. And so I'm going to store this energy, I'm going to put energy in with the motor, and then I'm going to get this powered push-off. And for the mechanical engineers in the group, this screen for some type of flywheel or spring system or something about trying to store energy over time and then get the big push-off, the big bang that you need for push-off. So it's quite surprising. Basically, you're walking here and you need a 250-watt push-off just to propel yourself forward. And you need 1,000 watts for running. And people would say, well, why not do this with a direct drive system, but you would need a really large motor and you would need a lot of electricity. You would basically need electricity to brake. You could store some of that, but it's hard to do, and then you would need that electricity again for push-off. So let's look again at this robotic tendon. If I look at the robotic tendon, this is literally my simple control law. I ask, what are the forces that you need for gait? So I take the moments and I divide by a lever arm to get forces. I ask, what are the gait positions I need for gait? The gait, the biomechanics people give me the angles. I divide by a lever arm basically and get the position I need. So I get the positions I need. I get the forces I need. I divide by a spring constant. A is the free length of the spring. And then XM is the desired position of my motor. So I tell the motor, follow this pattern, follow XM. Just move the motor back and forth during the gait cycle. I do PD control, position control, super easy PD position control, 1,000 times a second there. And then the question is, as a designer, well, what should K be? So you ask yourself, well, I know gait power, I know force time, I know the output power, I know F times XG, what should the input power be? Well, the input power is going to be the output power plus the spring power. And you never see F dot over K as a spring power because people don't talk to you about relative velocities. So F dot over K is spring power. And I want to choose K to reduce the peak power of the motor. I cannot reduce the energy. I'm not playing games. I'm not a perpetual motion machine. If I need 10 joules for the step, then I put in 10 joules. But what I can do is minimize the peak powers. I can basically say the motor's not going to have a 250 watt peak power. The motor's only going to have 70 watts of peak power. Because I am going to basically pull on that spring early, but the gastroc is pulling on the Achilles tendon early, and then pull, store energy, and then use that energy for push-off. So here's my little stick diagram. Basically, your foot lands. As you roll over, the human being is pulling down on the spring, and the motor is pulling up on the spring, and then you use all of that energy for push-off, and then during push-off, the motor continues to move upward as this side collapses. So it's the relative velocity between this side and this side. So I store energy in the spring, and then both sides, this side and this side, both move in that direction, and this side is moving slower than that side, so you're just naturally releasing all the energy. questions people have asked me in the past is, if I walk on my toes like this, then I'm not going to store energy in your system properly because you don't control the output side of the ankle. And I say, I agree with you. You can walk on my ankle like this, and it costs you lots of motor energy, but it also costs the human being lots of energy. I mean, you don't walk, around like that. So I basically set up a pattern, and the user, works in that pattern to store and release energy properly. So if I look at this robotic tendon, I have a roller screw here, the motor attaches here, and I have a nut pattern. So you'll see me now saying, this is the nut pattern, this is the input side of the spring, or the proximal side of the spring, and it's going to be going up and down, and the distal side of the spring is open loop. So the distal side of the spring goes up and back down and over, and my side of the spring, my nut pattern, goes down and then goes back up during swing phase. So I store all this energy in the spring, and then it gets released for power push-off, and then the motor picks the foot up during the swing phase. So the motor is doing two things. It's pulling on the spring to add energy, and it's picking the foot up during the swing phase. So why am I using springs? They're 300,000 watts per kilogram, and my motors are about 300 watts per kilogram. Springs are 99% efficient. They're super lightweight. They're economical. I purchased custom springs for $10. So you tell me your weight, and I basically get a Dremel tool out, and I purchase custom tools and cut the spring to your size. And they're naturally compliant, so I have safety built in. People like to ask this question. I am about an order of magnitude softer than the other ankles out there, the Biomedicals. I'm really soft compared to them. I'm storing energy in the springs and letting them go. So for the design people, basically, I've got this equation that says, here is my gait power, here's my spring power, that's going to equal my motor power. I put absolute values there because my motor is going to have to either hold the spring or push the spring. And basically, all I do is say, I know this. I know F and F dot, because F dot is the rate of change of the load. F is the load. I don't know K, so in any MATLAB simulation nowadays, I'll just vary K and see what the peak motor power should be. And basically, if you have a stiff spring, or if you're in the series elastic actuator range, stiff springs, you basically need 250 watts for push-off. If you're super duper soft, you're like pulling on taffy. So my motors would have to just pull forever and then push forever, and you'd be putting way too much power in. But there's a sweet spot where you could pick a nice stiffness, and then you only need about a 70 watt peak power for your motor. So basically, I'm reducing the peak powers by a factor of 3 or 4. And that means smaller motors, smaller currents, smaller motor controllers, all those types of things. So basically, I'm optimizing for the stiffness for an 80 kilogram person walking at a certain speed. Yes, if you were running, you would need a stiffer spring. So for running, we attach stiffer springs. So here's the punchline on the robotic tendon. If I was to do a direct drive system, basically I'd have to brake and then I'd have to push. So a direct drive system would have to brake or slow the person down and then push the person off. So a direct drive system would need 250 watts of peak power and would need 36 joules of energy instead of the 19 joules of energy. A robotic tendon, you could do two things for a robotic tendon. You could pick a spring so that the spring does all of the peak power at push-off, so the motor does nothing at push-off. Or you could pick a spring, and it doesn't matter really which case you pick, or you could pick a spring that minimizes peak power, and that's what we're doing right now, case number 2. So you could pick a spring that minimizes peak power, so you're down at about 70 watts. So now we're reducing the peak power by a factor of about 3, and our required energy is half of a direct drive system. So our required energy is in half, and our peak powers get reduced by a factor of 3 to 4 with the robotic tendon. And here is the, people ask, okay, in simulation, what's happening? So what's happening is the motor is pulling on the spring early, storing energy in the spring. So the spring is storing all this energy. And then the motor power plus the spring power add together to give me gait power. If you just take this curve, add it to the spring power curve, they add together to give you the gait curve. So the spring power and motor power add to provide the desired output power. Notice that 40% of gait, the spring and motor are working in opposite directions. So my motor is putting positive power in, my spring is storing energy in, and then my spring does most of the push off. The motor does the last, little bit. So the spring is providing about 80% of the push off power. So here is real gait data off of a treadmill. I just have ankle treadmill data. The ankle gets 9 degrees of dorsiflexion. This is on a amputee subject. I get 23 degrees of plantar flexion. The user has complete control of the ankle motion of the output side, and the output side of the spring is not controlled. So what's shocking about this plot is that I am getting, the blue is my data, the dashed line is my standard deviation, and what's shocking about this plot is the motion looks very good and I don't control it. And this is the data from Whittle. I just used standard Whittle's gait data. And this is the model, and this is the output motion, but my output motion looks very good and it's not controlled at all. So that's open loop. And they're just walking on a treadmill. And I'm getting nice powered plantar flexion. If I look at the moments, basically I just measure the spring, and as I said yesterday to some people, my spring is a poor man's force load cell. I've got a $10 load cell basically in my system, and I measure the spring deflection, which tells me the force times the lever arm is moment, and basically I get a nice looking moment. I've got a little bouncing there because I don't have any dampers in the system, but I'm getting nice 80 newton meters out at the ankle. And 80 newton meters is hard to get. I mean, you're really stressing the systems. I've broken springs, I've broken aircraft aluminum, I've broken a bunch of things. But we're up there 100. You're up there 100 newton meters. In the actuators, you can be up at 1,000 newtons in the actuators and things. So it's not an easy problem to solve. If I look at powers, this is a nice punchline. The red again is Whittle's gait data. I get peak powers of 200 watts. This is for a subject that does not weigh 80 kilograms. He was more about 65, 70 kilograms. So my desired peak power was only 200 watts for him. And I'm getting the peak powers that I want. I have, yes, a standard deviation between the peak powers, but I'm getting power amplifications of 3.7. The model was predicting 60, 70 watts. I'm actually was only about 40 to 50 watts of peak power out of my motors. And so this is a subject walking at 2.2 miles an hour. We're looking at the power at the nut, which is my mechanical power versus the power on the output side of the spring. In this one I had a 9 centimeter lever arm, and we were walking at 2.2 miles an hour. So my key accomplishments were that we had good ankle range of motion, we had the required power. The peak power is 3 to 4 times larger than the peak motor power, which means much smaller motor in size and weight. and it allows a highly active amputee to regain high functionality and gait symmetry. The robotic tendon stores and releases energy during the cycle. I use a tuned spring for each individual as compared to a traditional motor gearbox. And the proximal side of the spring uses robust position control, and the distal side of the spring is open loop. So I'll stop there. Now I'm going to talk a little bit about my controller. I do not use state-based control. I stopped on state-based control because I was building ankle orthoses for stroke, and they never landed the same way. You never got a good heel strike, or the foot would never land flat. And so we really struggled. So we gave up on the if, then, else state-based logic and decided to go with a continuous controller elevation angles. So this is a little controversial. Lacquaniti in Italy really believes in elevation angles, not joint angles. I like what he was doing, and it's what we're doing. Basically, we measure the shank angle versus gravity, foot angle versus gravity. I don't do much at all with the hips. But if I have someone walk on a treadmill and I ask you your elevation angle versus gait percent, if I ask you to walk slow, I get the blue line. If I ask you to walk faster, I get these other lines. But the problem is, if I look at my elevation angles, I got 10 degrees at 50% of the gait cycle, and I've got 10 degrees maybe at 85% of the gait cycle. So it's not one-to-one. So I said, well, what can I do? Well, what I could do then is make these, anyone in the audience who does control theory, I could make these phase plane plots. So I could ask the question, what is angular velocity versus angle? And I could ask the question, if you're walking with slowly and you've got a small stride length, I've got this, we call these beans. If I've got a fast stride length, I've got this. And basically, you got a heel strike, you go clockwise, then you land up vertically, and then you go around. And this is my phase angle, and I can watch this phase angle. So the phase angle is going to tell me gait percent, and the polar distance R is going to tell me stride length. And so I use a rate gyro, just one sensor for all the motion that you saw. I use a rate gyro. I integrate the rate gyro to get angle. I use a pseudo integrator, which you can look about. Basically, I get rid of the DC component. And I ask the question, what is the phase angle? And I basically say, well, what's my angular velocity? What's my angle? And I take the arctangent, and I get the phase angle. And the interesting thing about phi is phi has units of like 1/seconds. This is radians per second. This is radians. And so my angle has a frequency embedded in it. So I've eliminated time from my equations. And so basically phi is my metronome. And so it's very good because I can measure phi 1,000 times a second. So in the middle of the gait cycle, if you speed up, I speed up. If in the middle of the gait cycle you walk backwards, I've got some videos I can show later on that the person can walk backwards, can walk forwards, because I just watch this angle go this way or that way. Doesn't matter to me. Phi is my metronome. So an interesting thing about this too, lastly, is if I look at this bean or this bean or this bean or this bean, this is basically the same percent of gait cycle, the same percent of gait cycle, the same percent of gait cycle, the same percent of gait cycle. So now if I look at phi versus gait percent, all of those curves landed on top of each other. Yes, it's not perfect. I've had people say, well, I've used the word invariant. They say, oh, it's not invariant. You have some changes. But for an engineer, I can just fit a curve to this, and that's what I do. And so I just say that this is my polar angle, this is my curve. That tells me gait percent regardless of stride length. So I know my gait percent regardless of stride length, and then my polar radius tells me stride length. So basically my polar radius tells me where to be here. My polar angle tells me where to be here. And then this tells me where to be for my nut position. So basically, if you have a normal stride length, go up the curve and back down. If you're walking fast, go up the curve higher. So people have asked me yesterday when I want to walk faster, I basically am up higher on this curve, so I'm pulling more, so I'm giving larger forces. If I want to walk slower, I've got lower forces. If in the middle of the gait cycle you're walking slow and then you speed up, you basically just jump along the surface and slide over. If you're standing still, you're basically hanging out around here, so the motor's not doing anything, so you can kind of just sway with the robot and you're fine. So people have asked me, well, what does it feel like? And they say, the first things they'll say is, well, when I stand still, I can sway, and then my tibia is not being bumped into the socket, so I don't have pain here. I'm not tipped forward because I can just sway with the ankle, and I can stand the way I want to stand. The next thing they'll say is my back doesn't hurt anymore, and I think that's because you could pick the foot up nicely. And then lastly, it does give them a nice powered push-off. But those are the main things they say. So I no longer use gait curves in my lab. I use gait surfaces. So I've got these gait surfaces that I play with. And basically, I have one gait surface for walking and a different gait surface for running. Because the gait surface for running, I've got to take this and shift it over. Because for running, the push-offs occur more at 30-40% of gait cycle, not 50-60% of gait cycle. So I do have to have two surfaces, one for walking, one for running. So I'm developing a continuous-based controller based on tibia angle. My phase angles determine gait percent, regardless of stride length. The polar radius is the measure of stride length. The stride length and gait percent determine the proximal position of the robotic tendon. So we're just doing this. We just have a surface, and wherever you land on that surface, I tell the spring to move. And I don't change the surface for stairs or declines or inclines, because basically for inclines we're measuring the angle versus gravity. So I'm changing where I am on that surface automatically with my rate gyro. So my vision is to study kinematics and kinetics, to use springs, to do energy storage and reduce power and energy requirements. This is really more for the robotics people. I don't simulate compliance. I actually use a spring, and I use that spring for powered push-off. This is for the robotics people, I don't do fuzzy logic or state-based control. I just use a really simple linear position control law. I'm not restricted to joint control, so that's a little more to the biomechanics people. I use elevation angles. I do not use feedback control on the output side of the joint. So that was my second section of the talk. My third section of the talk really is now for you, which I've not done before to people, so this is my first time on this, is to ask, how could we do some peripheral nerve interfaces? Could a robotic system accept commands from the nervous system? So could you tell me where to be on a gait surface? Could you tell me how to pull the spring? And could a robotic system return force or position information back to you? So I've got ankle encoders, I've got spring deflection, it's a poor man's load cell, I've got FSR sensors, I've got things, and we're always going for this idea of volitional control. So people are saying to me, what can't I do? Well, you can't just stand up on one foot and move your foot back and forth. The guy that I was working with said, I'd love to be able to play piano again. So he'd love to be able to push on a pedal when he wants to push on a pedal. So I don't have volitional control. I can walk on inclines, declines, up and down stairs, jump, run, but I don't have volitional control. So let's talk about the most general control law that you could have for me. This is what I call equilibrium controlled stiffness. So I've got this same diagram as before. I want to control the motor's position. I can measure the ankle position. I could measure the ankle position. I could measure the actual ankle position, where it is. I could ask you, what do you desire? That's my nut control. I could ask you that. I could ask you what the forces that you desire, and I could ask you how you'd like to change the stiffness. So I could ask you, as peripheral nerve people, you could change the desired position. That would go here. You could modulate the desired force. That would go here. You could modulate the desired stiffness. That could go here. So let me give you some intuition on my controller. If you were to push in on the device and I was to push in, it would feel stiff. Even though this stiffness is completely fixed, I can make the robot feel stiffer. You know, yeah, okay, 5 minutes. So I can, if I push, like you push with 10 pounds here, and I have 10 pounds per inch, and I don't move my motor, I deflect 1 inch, and you said, it looks like 10 pounds per inch. If you push with 10 pounds, and I also push in a little bit, you'll say, hey, I only moved a half an inch, so you'll think that it was 20 pounds, right? You'll think that now the K desired is 20 pounds per inch. So I can make this thing feel stiffer. I can make this thing feel softer. Intuition, when you play baseball, you catch a ball, if you want to feel soft, you kind of go like that. So you're pulling back. If you want to feel stiff, someone pushes you and you push them back, you stiffen up. So basically I'm saying you can play with K desired, you could play with F desired, and you could play with XG desired. And the motor, and this is the desired motor command sent to a motor controller. So for the controls people, this is just my desired command sent to some PD controller that is embedded in the robot. So I can make this simple. I can make this simple and start simple. Let K desired equal K, which is exactly what I do for SPARKy ankle. Now I'm left with two terms. So if I let K desired to equal K, you tell me, peripheral nerve people, you tell me the forces that you would like, or you tell me positions you'd like, and I'll just move the motor back and forth. So if I just let K desired equal K, then that's my simple linear control law. If I let K desired equal to K, I get the simple control law. If I let K desired be infinity, I have a position controller. Basically, the position error goes into my motor controller. If I let K desired to equal 0, then basically I have a force controller. Basically, the motor, you move, the motor moves to follow your movement, and then the forces that you'd like, the motor moves to give you the desired forces that you'd like. So my controller is quite simple. If K desired equals K, I get the SPARKy controller. If K desired equals infinity, I have a position error. And if K desired equals 0, I can control the force. So I have a video that I haven't shown before because we're trying to get some grant money on it and haven't done it yet. But this is to show some volitional control. It's to show that if the user gives a position command to the robot, that, I've got a sensor inside the socket, I can move the ankle. So basically what I want to show with this video is I've got a simple system that I think could interface with peripheral nerve interfaces.
Got my leg back.
Wow. Can you try to hold the position as something in the middle? Oh, yeah.
Right, so he's saying I got his leg back, and it's the first time he said, hey, it feels like I can do what I want to do. He does not have sensory feedback, so he doesn't have any proprioception or any type of things like that. But I think this is where we all want to go.
So how is it getting leg?
We put a sensor inside against his tibia, and then he can vary that sensor. Think of it as a pot, and he's varying the pot. It's pressure type sensors. We're trying to do a provisional patent on the idea because of the gait market. But basically, you know, this is, I think, where we all want to be, is that the person can get the sense of his leg back. So I think that's, let me end here, say thank you. This is the National Geographic magazine. I like to end here. It took us 8 hours to get that picture. But, you know, they're not allowed to do any touch-ups or anything, and they had computer strobe lights to strobe with the person, and they, you know, spent about 8 hours to get that one picture. And they're not, because National Geographic is not allowed to touch up anything. Because I actually asked them to get rid of some of the dust or dirt or something, and they said, no, you can't. But he did a really nice job. There was ASU was up in the corner there, and you can barely see me there. So if you look at the whole picture that he got, it was quite a. Well, no. Yeah. I actually stood there for a couple hours actually, and he walked for a while. But so I'll end there. But that's the picture we've got. So questions.
Thank you very much for that fantastic talk. This is a small token of our appreciation for coming out to visit with us, and then an honorarium will follow as well.
Yes.
And we'll go ahead and do questions.
As a old mechanical engineer, I just love this design. It's beautiful, beautiful simplicity. What about the? I have a bunch of questions. I won't, you know, so just two quick ones. What about the weight of this device? Where is the weight? Where is that weight? Is it the batteries, the motors? You know, I assume is the majority of it.
Right. So the majority of the weight is in the motor here and the battery, and so we're putting the battery up at the waist right now. If commercially we'd put the battery up at the socket as high as you could. We are about a 3 to 4 pound device now. It is less weight than the amputated limb, but people still say it feels heavy. And I think it's because you put your leg up here and you say, oh, it doesn't feel heavy, because the human being is naturally doing gravity compensation. You know, you're pulling on springs doing gravity compensation. When they put it on, they'll say it feels heavy. As soon as you turn the motor on, they say that they love it.
Most of the weight is in the battery rather than the motor, or how does that?
The battery is 300 grams, and my motor, the battery is about 300 grams, and my motor is 300 grams.
Just real quick, does fitting change? Does the usual fitting that you use with a prosthetic device in the interface, you know, become a more critical issue in this design?
You need a nice fitting because you don't want slippage going on here because I'm giving you a nice powered push off. So we've tried compression sleeves, we've tried, and I'm sorry, I'm not a prosthetist. The pin joint systems we've tried the vacuum sockets. You want a good fit. Active military amputees, they've said that this is perfect. They love it. They want it. If you've got some, you know, peripheral neuropathy and diabetics, you better be careful of that skin interface. You know, so you want a nice fitting. But it's, you know, I've never done a long-term study with diabetic patients, but that probably should happen.
I'm sorry.
Have you looked at the any metabolic advantages to using this device?
Yeah, so we have, and basically your metabolic cost is about 30% higher wearing a passive ankle. Our metabolic cost is back to normal or even slightly below normal. I've told this to people, and has found the same thing, where people start to pull more energy out of the prosthetic leg. So they'll start to use less energy on this leg and start cheating and start pulling energy out of this leg because they're basically pulling joules out of the battery. So you need to cap your device.
The ankle is complicated. There's 3 degrees of freedom there, and you're only using one. How come then the movement looks so natural?
We also have the ankle joint. We copied the prosthetics market, the ankle joint sits on rubber bushings, so we get a little bit of this. Yeah, so we do that. We have a design. We gave it to the Army to do 2 degree of freedom ankle. We never got funding to do that, to do a 2 degree of freedom ankle, because you need 2 motors, double the electronics.
Most of the power during slow walking comes from hip flexion. Only when the speed increases, the plantar flexion becomes more prominent. So I'm wondering, did the self-selected walking speed increase in this particular subject? And if it did, by how much? And was the mode of increasing speed increasing cadence or increasing step length?
I can answer a couple of those questions. One of the subjects walked at about 1 mile an hour with this passive, per second, and then he was up at about 3 miles an hour with the device. So like, what is that? About 1 meter per second. So and then this person who's more active can walk a lot faster. So the self-selected pace did go way up. I can't tell you, I didn't do the Gait lab studies, whether it was stride length or stride frequency. I assume it was probably a bit of both, but I can't tell you definitively on that. But self-selected pace did go way up, and such that the diabetic amputee that we had working with us, he lost 10 or 15 pounds with us because we had him walking 3 times a week. And he was walking, 3 to 4 miles an hour, and most of the time he was just sitting at home. And he even said that he was just sitting at home he said he was just sitting at home watching TV. And here he would go to the lab 3 times a week and exercise. It was like an exercise regimen.
Well, you said their energy consumption went down, so I would assume the energy consumption went up as they started walking faster.
Yeah, but I mean,
But it's at the same speed it would go down.
Right, at the same speed it would go down.
The controllers really all get, I just had a question about it. Your elevation curves, are those universal, like use the same curves for all the participants?
So we do use we are using the same nut pattern for all the participants because I have a very soft spring. But I do change the spring per participant.
I guess thinking toward the future, how do you imagine switching states from those curves to volitional control?
Well, what I'm hoping is the volitional control, I'm thinking out loud, that the volitional control will either tell me where to be on that surface, or I could completely change and say, I'm not going to do surfaces at all. The volitional control will just tell me F desired and tell me XG desired. And then that just tells me desired position.
So in that video, there's no elevation curve.
Elevation curves. I mean,
you turned that apart.
Yeah, no, that literally was just using a sensor to control that.
I just think it'd be interesting to see if those curves change over time, or how the device affects those curves. Because those are just from unimpaired individuals.
Right. I'm using an average of unimpaired individuals. I am.
Tom, I guess I have 2 questions. One is the use of the spring makes a lot of sense, and you've shown really compelling results. It seems to me that you pay a price for that in terms of size. I mean, the spring has, you can only make the spring so small.
Right.
And some of the other power ankles are sort of self-contained.
Right.
So how do you, can you envision a way to reduce that size and maybe have a wearable underclothing?
Right. So we went to. So people told us. So let me escape out. I wasn't going to show a commercial. Here's a commercial. So people said they didn't like the springs on the outside The jack spring is I can tune the spring naturally. And then this is the Odyssey ankle. So this is kind of what they're commercially going towards. We use one spring. The one spring is hidden in there, and then the motor's there. And so this isn't under the closed system. So we got rid of the two springs on the outside and put a one spring on the inside. And so Spring Active is trying to commercialize an ankle.
Have you noticed how do users transition from sort of a standard carbon fiber attachment that they use every day to this device? Is there a learning?
So, and I'm not lying on this. So in 5 minutes, they're walking on this device and loving it. And then when they take it off and put on their traditional foot, they kind of stumble around a little bit and get going. And what he told me was, it's like wearing rollerblades. So wear rollerblades for a half an hour, and then you take them off, and your body feels a little funny. And then after about 15 minutes, you're walking around perfectly fine. So it takes them about 5 minutes. Because I just put them in there, use a rate gyro, set the springs up, and let them go. I don't try to do lots of fitting parameters or tuning parameters. I can get you walking in 5 minutes. And as soon as they stop on it, they say, oh gosh, I have to relearn how to walk with the passive system. And Professor Goldfarb has said the same thing, where he basically has to teach them to walk properly with his motorized knee device. And when they take it off, he has to teach them how to, again, walk with the passive device.
And are there special challenges? My second question. Are there special challenges to incorporating this sort of concept into an orthosis where you don't have the volume that's vacated by the amputated member?
Right. So the orthoses, the best job we've done on the orthoses, if you were to have someone to come in, they could just put their foot in there. I could change the lever arm length. If you're really heavy, I need more oomph. So, or you could maybe try to put something inside or something on the outside. So in orthoses, I would have something that kind of sticks out a little bit. But I think the benefits are quite good. And the surprising thing is, it used to be people wanted to hide their device, but the soldiers that put this on, they want to wear shorts and show it off. I mean, it's a completely different mentality and thinking. They want to show off that they've got the coolest robot. Right. But I'm serious on it. People told me, oh, they'll never wear this because they don't want to wear something. And now they want to wear it. Because it's...
Cut here real quick. I'm sorry.
Oh, okay. One last one? Or?
Yeah, go ahead. Let's do one last one and then we'll... What's the limitation to making it smaller then? I mean, you're saying you're running a very soft spring. Is the limitation then in the roller screw of the motor?
Yeah. I'm using a $3,000 roller screw, $500 motor. I'm using the best stuff I can, and mechanically we're just not as good as the human being. I mean, we just don't have the power to weight ratios, force to weight ratios of muscle. I mean, human being is great. In that sense.
Thank you very much.
Okay.